Hello, my name is Michael Robinson, and I'm from American University. I'll be telling you about using some statistical techniques to identify files that are non-compliant with a consensus file format. I'd like to thank my collaborators at BAE Systems and my student, as well as the data providers that you'll see in this talk. And finally, I'd like to thank Sergey for organizing LangSec and also for the funding. Suppose you have a bunch of files that supposedly comply with a particular file format and a set of parsers that consume files complying with that format. And those parsers generate a set of error status messages for each file. The questions that I'd like to address are, is there some kind of consensus as to which files really comply with the format? Are the parsers detecting the same thing? Are there bugs in any given parser? And is the format well specified, even partially? Can you find me files that are corner cases in the format? The key points of this talk is that statistical techniques work rather well for this task. Now, you may hear that statistics is good for probability. That's certainly true, but statistics is really for ensembles, and that works even for deterministically generated data. Of course, you hope that when you run programs on your computer, it is deterministic. And so even though we're using statistics, we're using it for ensembles. I argue that format consensus is an ensemble property jointly of the files and the parsers that read them. And so if you're looking for places where files are compliant or not, or parsers or buggy or not, statistics is a good place to start. I'm going to show you 3 easy-to-use statistical tools. The first and third of these are actually quite standard, but have apparently not been used for these kinds of tasks. The source code for these is actually not something I need to show you because they're easily available in a few lines of your favorite data analysis programming language. And the middle one, the Bernoulli misclassification test, is a novel test that I'll show you that helps you identify files that deviate from the consensus. The file format that I'm mostly going to be focusing on today is PDF. It's a file format governed by an ISO standard that's written out in English. It's not machine parsable. There's no reference implementation. Even though Adobe was the start of PDF, Adobe is no longer the only game in town. And there are many different parsers with different code bases that consume PDF files. They make some different choices when the format is ambiguous. And when the files are not compliant, the parsers often try to fix those files. That's not governed by the standard. And you get differences in behaviors there. Of course, parsers are being software, can have bugs. And so the takeaway is you can't trust any individual parser to tell you unambiguously whether a file satisfies the PDF standard or not. But an ensemble of parsers should generally be more reliable than any single parser. We'll see that in spades here. The data I will focus on in this talk was produced for the DARPA SafeDocs project and the Evaluation 2 exercise. Consists of 10,000 files that are ostensibly PDF files. Most of them came from Common Crawl. Our team ran just shy of 24 parsers, or individual parsers with various options, against each file and captured the standard error that was produced. Separate from us, the files, every last one of these files were manually, and heroically I might add, marked as being either compliant or not, valid or rejected according to the PDF standard. They were given to us in 2 separate data sets, an internet-sourced and a dangerous data set, which is somewhat ominously named. The internet-sourced set had 9,000 files, the majority of which were valid PDF files, as in valid according to the evaluation team's manual marking. The dangerous set, a slim majority, were rejected. What does that mean for the valid but dangerous files? Well, probably you don't open them, I guess. Now, regardless of whether you're using PDF or any other kind of standard that's governed by a format, you could do this kind of ensemble analysis. Works for any kind of process. You don't need the parser source code. If the files are dangerous, they're encapsulated in a Docker sandbox, so if anything goes bad, well, it doesn't take down your server. How does this work? Well, you take every file, you run it against every parser. This spits out what we'll call an error matrix. You could do some standard statistical analyses, the principal components analysis, and the correlation analysis on that single error matrix. Or if you have two data sets, as we do, you can exploit their differences using the Bernoulli misclassification test. What is that error matrix? Well, it's a Boolean matrix in which each column is a file and each row is a message regular expression, i.e., an indication of whether a particular message occurred or not. So you put a 1 in there if that message is present, a 0 if it's absent. You need to manually build these regular expressions. Our team spent a lot of effort doing this. You could certainly add rows for other features, return codes, contents of standard output, renderings, etc. We did not. We just looked at standard error. Our experimental hypothesis is that anomalous files or parsers, those that deviate from the standard or the Ensembl, will be manifest within the context of this relation. That certainly appears to be true. Each of the rows in these two matrices here are the same. They're the same message regular expression number. There's over 900 of them that we have in our data set. Each of the columns are the files. Those are different between the two data sets. A black pixel means that that message was present. It's a 1 in the matrix, and white is a 0 in the matrix. That message was not present. If you grab a particular column, you can see which particular messages were fired for that particular file. So here there's a bunch of Caradoc errors and a bunch of uncategorized errors. These are places where our regular expression coverage wasn't so good. This particular file was deemed as valid by the evaluation team, so even though that Caradoc found some errors, it's still valid. If you look row-wise, you can see that there are some dark bands. Much of this is due to a lack of good regular expression coverage on our part, but some of them are just due to the fact that some parsers are noisier than others. Let's try to visualize this. The standard way that you visualize this kind of thing is with principal components analysis. What you do is you grab each column and you look at the pairs of columns and the Hamming distance between them. So you convert your error matrix into a distance matrix, and then you imagine that each of these columns, files, are points in space and try to generate a scatter plot. Principal components analysis is a standard way to do this. If you run principal components analysis on the two data sets, here's what you get. I've marked the valid files in black and the rejected files in gray. You can see the texture is quite different. The internet sourced set is very clumpy, and the dangerous set is more spread out. I have a going hypothesis that we're deep in the research to figure out if this is true, that clusters correspond to separate tool chains, i.e. perhaps one of these clusters is Adobe's official Acrobat, perhaps one of them is PDF LaTeX, perhaps another is OpenOffice, I don't know. Still very active. But this suggests that there's a lot of structure present in these matrices. Let's try to exploit the difference between the structure that we just saw to identify valid and invalid files. How do you hope to do this? Well, what we'll try to do is imagine that the internet-sourced data is largely a collection of positive examples, since the majority of those files are valid. A slim majority of dangerous files are rejected, so let's think of those as negative examples. Trying to put these two together means that we have to deal with the files that aren't in the right place. They're misclassified. So the files that are in the internet source set but are rejected really ought to be removed if you want a set of positive examples. Conversely, perhaps counterintuitively, the valid files in the dangerous set are misclassified as well. How do you find these misclassified files? Well, you ask, is a given file's pattern of messages more characteristic of the ensemble it's in or the other ensemble? There's a classical statistical test for this sort of thing, a likelihood ratio test. We're going to make a bunch of assumptions. Turns out both of these are wrong, but it seems to be okay. The messages either happen or they don't. We assume we have a Boolean error matrix, a 1 or a 0. Certainly, if you get duplicated error messages, you might want to put a non-Boolean value. This doesn't happen very often in the data. I went through and figured that out. But if it were to be frequent, you'd use a different distribution instead of the Bernoulli distribution. And the other assumption is the messages are statistically independent. They don't influence one another. This is definitely wrong, but it also doesn't seem to impact our accuracy too much. Still an active area of research. How do you do this kind of ratio test? Well, you row-wise figure out the frequency of each of these errors, the relative frequency or the probability that that error message occurred. How do you do that? Just take the average, the mean, row-wise. So here's the average for the internet sourced files. Do this for the other as well, so the dangerous files. You can see that these two functions are rather different. The probabilities are different for each error message. So for a given file, then, you can aggregate those probabilities. This is where the independence and the Booleanness assumptions come in. You say, what's the probability that a particular file came from one dataset or the other? And then you ask what the ratio of these probabilities are. If the ratio is high, it means that the file definitely wants to be in one set or the other, in particular wants to be in the other set. So the large values occur for likely misclassified files. Here are histograms for the two data sets. So the horizontal axis are the files sorted by the statistic, the likelihood ratio on the vertical axis. You can see that there's some twists and turns. Those twists and turns due to the fact that our data are clustered differently. So the fact that the clusters are rather tight in the internet sourced data gives rise to that particular sharp knee. And the more spread outness is why the progression of the histogram is a little smoother on the dangerous side. I've marked the likelihood ratio of 1, horizontal line lambda equals 1 for you, so you can see where that is. And so the Bernoulli misclassification test says that the files that are less than that in the internet sourced are likely to be classified correctly, i.e. valid. In the dangerous set, it's backwards. Those files with a large likelihood ratio are likely to be in the wrong place, i.e. not dangerous, i.e. valid. How does that compare with the ground truth? Well, for this particular threshold, the internet source isn't so bad. The dangerous is a little wrong. But this is for a particular threshold. Maybe if we tweak the thresholds a little bit, we could do better. Certainly true. If we were to identify the optimal threshold, which, by the way, we do not know, we can actually do quite well. We can hit 95% of the internet sourced files dead on, and the dangerous files, about 80% of them we can get as well. Finding that threshold is still an active area of research. Okay, so one thing when I give this kind of talk, everyone asks, do you really need all those parsers? And, well, most of them, yes. And the reason for that is actually relatively easy to see using principal components, but not by files, instead by parsers. So if you look at the parsers, i.e. rows, well, those are error messages, not parsers. So let's group up all the error messages for a particular parser. Fine, that can be done using a little statistical magic. You can build a principal components analysis plot. Each point on the right is a parser, or a parser with given options turned on or off. You can see that there is a tight cluster. Those parsers more or less have the same kind of behavior. And there's a bit more spread out region that sort of spans everything. We're aiming for redundancy with this methodology, so we want the spread. The cluster, we can just pick one out of. The takeaway here, if we look at the underlying distance matrix that gave that principal components analysis, the takeaway is that parser diversity is essential. You want low correlations amongst the parsers because that's more informative. The higher correlations mean that you can kind of predict what the error messages from one parser are, knowing the error messages for the other. So they're not quite so informative. Roughly speaking, of the nearly 24 parsers we needed slightly over half of them in order to get good results. What's next on the docket? Well, we have some theoretical questions about performance and stability, some methodological questions about dependencies or how certain richer features might work, as well as some questions about clustering and about how to come up with these regular expressions that we relied on so heavily. If this happened to spike your interest, there are a bunch of papers that you can read that I've written on the topic, as well as some software you can play with for the Bernoulli misclassification test. Hope this was informative, and I hope you enjoy the rest of LangSec. It looks to be very enlightening and interesting.